Okay, ladies and gentlemen, dear colleagues and guests, welcome to Faculty of Electrical Engineering at CTU. It is my honor to welcome Professor Neil Gershenfeld from MIT. I was lucky to had a great opportunity, thanks to Fulbright scholarship, to spend 10 months in Center for Bits and Atoms, CBA, which Neil leads. CBA breaks down barriers between world of data and world of matter, from quantum computing, Internet of Things, to personalized fabrication and digital materials. CBA also inspired creation of more than 2,500 Fab Labs in 150 countries, giving people around the world tools to make almost anything, which happens to be also name of Neil's famous course at MIT. Neil was recognized as one of world's public intellectual leading and described as modern-day Leonardo. To me, one quote of his stands out. Computer science is one of the worst things that ever happened to either science or computers, which I think reflects his vision or idea that we shouldn't separate digital information bits from physical world atoms. So today in his talk, he will take us on journey from bits to atoms. If you have any questions, you can either use Slido, or Neil told me he will be happy to answer the questions interactively. And now join me in welcoming Neil Gershenfeld. Thank you.
Well, you're doing such a good job explaining me and everything we do. I feel like I should just sit down and let you give the talk, but I guess I will. So I lead the Center for Bits and Atoms. It was created to study how digital and physical relate. And so over the years, we've done things like the first faster than classical quantum computations. We did Grover's and then part of Shor's algorithm. We introduced cryptography in materials, computing and microfluidics. We were part of creating the first synthetic life, the minimal synthetic organisms. Part of starting Internet of Things. We did the first negative index left-handed materials. All of these things right at this boundary of digital and physical where you can't separate hardware from software. And so I'll give you a little background, and then the main thing I want to do today is talk about the areas of intersection with Yuri and our past, present, and future collaboration. So focusing in on work on robots. So the reason I'm here is this. I'll tell you about Fab Labs, and there's a global network, and we're gathering this year. And so it was hosted in Brno and Prague, and we had people from 55 countries for an intense week of incredible workshops. And so if you go to fab25.fabevent.org, you'll see all of the presentations and all of the videos. And there's an amazing group that included formal institutions, but to a great extent was grassroots, informal hacker maker engineering that isn't as visible perhaps in Czech Republic, but is world leading, world class. And so there's an amazing network, if you're not familiar with, to learn about the hosts of this gathering and what's happening in your backyard. Really wonderful experience. So the Fab Lab network that this was the gathering for was something I started by accident to help tell people about the research we're doing on digital fabrication. I set up a mini version of my lab, a Fab Lab, and the picture in the upper left is Vestmannaeyjar, Iceland, a small volcanic island off the coast of Iceland, as an example. And it includes the 3D printer, but it includes all the other machines to make useful things. So large format machining, precision machining, vinyl cutting, molding, casting, PCB fabrication, surface mount rework, embedded programming. And so with that, you can make all the things on the upper right, and those accidentally went viral. They're now in 150 countries, as far north or south as you can go on Earth, as rural as is urban. We didn't plan all of that. It was just this viral spread of access to it. Let's see, this is a picture of one we ran at the White House that's led to legislation for universal access to digital fabrication as a new kind of right, a human right. A colleague who became the city planner of Barcelona started an initiative for cities, instead of taking in products and producing trash, to have means of production as part of urban infrastructure, for cities to sustainably produce what they consume. And instead of having jobs for work for money to buy things, providing widespread access to the means to make things. And so that's all part of this Fab Lab network. And the meeting was all about that. And you can learn more about it through the fab25.fabevent.org site. But all of that came out of this, which is to teach my research students how to use research tools. I started a class called How to Make Almost Anything, and it was aimed at a few research students, and I wasn't prepared for every year hundreds of students try to take the class. And it's very different from a normal MIT class. Students do projects integrating these. Kelly was a star the first year I taught it. She was a sculptor without traditional engineering background, and here was her class project.
Hi, I'm Kelly, and this is my screen body. Do you ever find yourself in a situation where you really have to scream, but you can't because you're at work, or you're in a classroom, or you're watching your children, or you're in any number of situations where it's just not permitted? Well, Screen Body is a portable space for screaming. When a user screams into Screen Body, their scream is silenced. But it is also recorded for later release, where, when, and how the user chooses.
And going into the main building, up to the second floor. 저는 그냥 가려고 우리 나눠서 펜좀 가셨어요?
This was a web browser for parrots. This was an alarm clock you wrestle with. This was a dress that defends your personal space. And these happen so frequently. I realized the students were answering a question I didn't ask. I was answering how to do digital fabrication, go from digital physical, but not really why. And they were showing the killer app of digital fabrication is like personal computing. It's production for a market of one person. It's being able to produce what you want, not immediately producing industry mass production. And I was delighted this sort of outlier class being recognized as one of the most important contributions to learning at MIT, even though it's not a rigorous formal class. It's just learning to make stuff and doing what you want with it. So the reason I had to teach that class was the lab I run was started with a proposal to assemble tools to make anything of any size. So nano, micro, meso, macro, we have tools to make and measure. And the idea is they're all integrated. Rather than being separated by discipline and length scale, they're in a connected workspace where you can span across them. And so I had started the class to teach students how to use the tools, not expecting this passionate response. And then the passionate response to the class, which was started for the tools, was what then inspired starting the Fab Labs, and we didn't expect that global response. So to help facilitate that transition from digital fabrication as big centralized machines, we started working on rapid prototyping machines. And so that led to a number of companies. So Form Labs is one you might know. Ultimaker actually came through this. Bantam Tools, Fablight, Shaper, HandyBot. were all companies we started to make faster, better, cheaper digital fabrication tools. But my real interest isn't that. So if you think about stage 0 as MIT invented computerized manufacturing in 1952, and my lab has machines that are the descendants of that, you know, few $100,000 giant machining centers. Stage 1 is the Fab Labs that are kind of like the mini computer era. Then the step after that, the equivalent of sort of the hobbyist era, is this is all rapid prototyping of rapid prototyping. So I have a couple students with me. Quentin is one who's one of the leads on this, working on rapid prototyping of rapid prototyping, so rapid machine building. So these are all versions of Fab Lab tools made in Fab Labs. And doing it that way makes the skills and jobs local, which is nice. It avoids all the problems with customs and import and tariffs, because you're just bringing in the building blocks. But more than that, the machines don't all need to be the same. You can adapt the machines to local needs. And to do this, we've had to revisit all of the standard assumptions in CAD, CAM, machine control, and motion control, lurking behind this rapid prototyping of rapid prototyping. So in this world, you don't go to a Fab Lab to get access to the tools. You go to a Fab Lab to create the tools, democratizing the machine building. And so this is an example of that. Quentin works with my student Jake, who in this project we were working with the US National Institute of Standards on a national US initiative on advanced materials. And there's a big outer loop from developing a material to characterizing it, to learning to design with it, to process it, to use it. And so if you want to, for example, on an FDM printer, 3D print a new material, there's about 100 parameters you need to set. And they're tightly controlled, which significantly limits the use of recycled and renewable material. So in this example, this is a 3D printer, but unlike a normal 3D printer, instead, let's see, the state of the art was to do rheology first, so measure polymer flow properties and then turn that into what you can send to the printer. And here what we did instead is we made a printer that does rheology. So the printer measures forces, flows, diameters, all the properties of the print process. It's not a direct rheology measurement, but it's an indirect run of derived properties. Then the machine architecture is very different. All a stepper knows how to do is make a step. All a thermistor knows how to do is report a temperature, and there's no controller in the machine, it's just a real-time network. And then there's 6 or 7 levels of control. So first, you need to learn to make a step, so characterize a motor. You need to learn to accelerate and deaccelerate and learn inertial properties. You need to learn how the axes coordinate for kinematics. Then you need to move them and learn about dynamics. Then you get into the speeds and feeds, so flow rates. Then you need to link the rheology flow properties to the path planning properties, which is, these are each usually done completely segregated. And in a conventional machine, those are all baked in. So if you change any one thing, you need to completely change the internal configuration. Here, instead of sending a file to the machine is just a real-time network, and it's actually generating much more data than we're sending in. And then in real time, we're building adaptive models of the print properties. And so we showed we can recover the heuristics for printing existing materials. You can actually print much faster, much more effectively than the heuristics. And then we can take all sorts of recycled and renewable materials we've never seen before and figure out how to print them. And that's from killing off the historical CAD, CAM, machine control, and motion control boundaries and turning machines into open architecture. It's very similar to BitNet versus internet in the history of networking, turning machines into open architecture networks. And so this was a nice application of that. But along with saying computer science was the worst thing to happen to computers or science. And the reason I said that is it segregated hardware and software, and things like the development of quantum computing didn't fit that taxonomy. I've also, I'm on record for saying I don't like 3D printing. Having started 3D printing companies and doing research on 3D printing, I don't like 3D printing. And the reason why is compare state-of-the-art advanced machining to a child playing with Lego bricks. With the Lego bricks, you don't need a ruler to place them because the metrology comes from the bricks, so there's no build volume limitation. The Lego tower is more accurate than the motor control of the child because you can detect and correct errors, unlike a 3D print that can turn to spaghetti or machining operations where errors can accumulate. You can join Lego bricks made out of dissimilar material. It's hard to do very dissimilar 3D printing. And there's no Lego trash. Trash is an analog concept. Trash means materials don't contain enough information to be able to reuse them. You don't throw away Lego. You can disassemble and reuse the parts, unlike just about any kind of advanced manufacturing. Those differences have two kinds of precedents. This is exactly what Shannon taught us about communication and von Neumann about computing. So analog phone calls degraded with distance. Shannon introduced information theory, and one of the core results is if I send you a symbol instead of a wave, for a linear increase in the physical resources representing the symbol, the error in decoding it goes down exponentially. So there's very few exponentials in all of engineering, and that's the most important one. That exponential fidelity is what lets unreliable devices communicate reliably. Then von Neumann applied that to computation, showing how unreliable devices can compute reliably. And then the application of that, so digital doesn't mean 1 and 0. Digital means state restoration. And the application of that to fabrication is actually a little older. It's 4 billion years old. That's the evolutionary age of the ribosome. Chemical synthesis has an error rate of about a part in 10 to the 2. Elongating a protein in a ribosome is an error rate of about 10 to the minus 4. DNA replication has an error rate of about 10 to the minus 8. That's the exponential scaling of error detection and correction. And in the ribosome, it's in fabrication. It's coding construction. And that's what makes possible the exponential complexity of us. So in this roadmap, what I really care about is not additive versus subtractive. It's analog versus digital, the transition from printing and cutting to assembling and disassembling. So we're looking at that at a number of scales. One of the places where I started looking at this was I was approached by the aerospace industry about the problem of joining wings of a jumbo jet. So when you have giant composite wings and you need to stick them onto a giant composite body, the joints are a vulnerability. So we were asked, can we find a better way to stick them together? And the conclusion was, instead of making one big joint, to make lots and lots of little joints. And so in this paper, what we showed is this is oriented layup of carbon fiber. This is a cube octahedron. This is a structure that's right at the boundary between being under-constrained and over-constrained. And this was state-of-the-art then for high modulus ultralight materials, and produced in tiny volumes, in like, a centimeter volume by laborious printing. And by linking these loops of carbon fiber, we increase modulus in the ultralight limit by an order of magnitude, but with bulk samples, we could produce as much as we wanted. And so this is what started me thinking about the idea of digital materials, meaning a discrete set of parts reversibly joined with a discrete set of relative positions and orientations. So think Lego bricks or ribosomes. And so a long-standing goal for aero systems was pure lift and roll. So going back to the early Wright brothers planes, instead of rigid control surfaces deforming the whole airframe, is much more agile and much cleaner aerodynamically. The problem was morphing aerostructures introduced a lot of weight and complexity into the mechanism. What we did here is, this is the size of NASA Langley's biggest wind tunnel, and we made a morphing aerostructure this size just by linking these little parts. I was admiring your composite airplane in the courtyard. There's probably a year's worth of work on the tooling for the forming to produce those parts. Here, there's no tooling. We just link these little building blocks together and get state-of-the-art material properties in this deformable aerostructure. This was an exercise we did with Toyota, where they have they're part of a contest for extreme efficiency cars. And they spend, again, a year on the tooling to make the composite vehicles. And in about a month, we made one just by snapping these parts together. And in fact, this one was fun. On the race day, it was raining, and we did a bad job on the visibility, and the car immediately crashed. And everybody came running concerned, and to everybody's shock, including ours, the whole car just completely deformed around the crash. The sort of whole structure took up the elastic energy and just returned back, and the car and the driver were fine. This is a project we've been doing with NASA, looking at doing this to build structures in space this way. So far I was showing you CFRP and GFRP composites. Right now we're in a discussion to build a city with Bhutan this way, and I'll tell you more about how we're going to build the city. And here what we're looking at is net shape production of sustainable biovoxels. So starting from forest products to produce biopolymer resins and fibers that can't quite match the state-of-the-art material properties of the carbon fiber, but is completely sustainable production of the voxels. And then next door to this was Airbus approached us about using this to make critical flight surfaces. And for a jumbo jet, there's what I was showing you is discretely assembled, but mathematically it's what's called a truss lattice. And there's no material you could make the truss lattice out of that could withstand the loads, the critical aero loads of a jumbo jet. And so that led to this offshoot, where instead of truss lattices, we're making plate lattices. It's still discrete modular construction, but the plate lattices recruit more of the material, and they can approach the theoretical bound for just the bond strength limited. And so this is a way to make discretely assembled very high-strength structures by cutting, folding, and assembling. And see, I don't have the picture here, but Alfonso, who Yuri's met, has been doing fun stuff. He made a sculpture for an art installation, not quite, but almost the height of this room in an afternoon by cutting and folding these kinds of structures. So then the next step is, in this paper we showed, by changing the part type, this is rigid, that's flexible, that's auxetic, meaning it's a negative Poisson ratio, and that's chiral, meaning when you load it, it twists. Those are specialized material properties that have a lot of applications. Here, it's all the same base material. Those are individual parts, but once you get up to about 3 cells, if you put it in an instron and a stress strain tester, you don't see the separate structure. It just behaves like a bulk material. And so these are mechanical metamaterials, but what they let us do is tune very anisotropic material properties by having the same base material and just by varying how we assemble them. And so many years ago, MIT made a famous project called RoboTuna. Tunas are shockingly efficient swimmers, and they do it in an incredibly subtle way, which is if you paddle a canoe, there's a vortex that comes off your paddle that's induced drag. What the tunas do is they actually launch that vortex around their body, it comes around the other side and it becomes lift. And so MIT engineers made a robot that could do it that was made up of like 1,000 parts. And here, roughly not quite, but roughly in an afternoon with these building blocks, we made something equivalent to Robotuna. And this was a project where we developed all sorts of robots this way, where if you just look at this one, gray is rigid, purple is flexural. Assembling that way makes a structure that's load-bearing in one direction, but soft in another direction. That then lets you make a leg, and then with a few of those, you can make a walking robot. But there's no discrete joints, there's no tooling, it's just assembling these very simple components. And then this is one of my students with NVIDIA developed an environment to simulate these structures, and in particular to design them. And so this was a zoo of discretely assembled modular robotic systems. And one of the things we haven't done, and let me step back to explain, MIT has a program for international collaboration that doesn't support big research programs, but it supports travel and collaboration. And we're launching one of those between my lab and Yuri's lab. And one of the candidate things we're looking at doing is we have an environment to design, model, and build these, and we haven't done anything interesting in how to control them. For example, let's see, I don't know I have it here, but there's one that sort of looked like this, where when we made it, it just flailed, and we discovered if you put it on its back, it actually walks. And so a potential part of the collaboration is going to be adaptive controls of reconfigurable discrete robotic systems, where you assemble an arbitrary one of these, and then you need to figure out how to make it move. And it's a lovely problem that we haven't done anything on. So then the next step is how you build these systems. And here there's a beautiful connection between a material robot system. So this is a low degree of freedom arm, and it locomotes on the structure, it error corrects on the structure, and it navigates on the structure. So it can't work autonomously, but it can do all of those functions on it. And in particular, it's missing most of what goes into robotic control systems, because every single step it re-registers. And so the lattice plus the robot dramatically simplifies the robot to make this into a robotic assembler. And so this is a design study we did with NASA to make the world's biggest space structures. So we looked at both what are called star shades and telescopes for, this is path planning for swarms of these assembly robots. And so what we're looking at doing, that's still in a very early stage, is the Webb telescope had 300 single points of failure, any one of which could kill the whole billion-dollar project. Instead, we're looking at you flat pack the structure with the faces of these voxels, and you flat pack the robots in a way I'll explain, and then you assemble the robots, and then you incrementally build the structure without single points of failure. This is the current state of that. So this is a version of the robotic carrier with a design tool that lets you design a structure. And then this is a slightly more complex version of the robot that can both locomote and tow and place parts together. And so that's what the current generation looks like. And we've done a number of versions of joints. So like the NASA wing was, let's see, the Toyota car was rivets, the NASA wing was tiny fasteners. This one is using bistable mechanical latches. But designed properly, the joint sort of disappears. It's only a small part of the total. The structures don't fail at the joints, and they're only a small part of the weight. But this is a current generation of one of these assembly robots, and this is what we're looking at in a collaboration to essentially build a city this way, to build large-scale structures that crucially are, so they're made sustainably out of biomaterials, but the structures themselves are reconfigurable. You're doing a big construction part project here that maybe the building was built 100 years ago, and after 100 years ago, you tear it apart. In this world, the structures are reconfigurable. You can continuously remove and add parts and grow them and change them. So the next step in is these are voxels that transmits power and data as well as forces. So there's a few different ways we've done these. Aluminum is used as a PCB stock for heat transfer. Here what we're doing is we're using aluminum circuit boards to make functional voxels. And so here, when you assemble the structure, there aren't wiring harnesses. The intelligence is built into a structure. So this was, for example, an interactive load sensing structure. Airbus had $1 billion fault with the wiring harnesses in the A380. Here, if you can build with functional voxels, the structure builds in the intelligence. And so with that, this was a small test. This is a drone without wiring. So what you're looking at is the entire drone. You assemble the parts, and then the drone can fly, and there aren't wires to pull through it. And so that leads to this, which is with the functional voxels, you can make the assembler out of the parts that it's assembling. And so this is a design tool for that, where a robot has a feedstock of the functional voxels, then can locomote and start placing them. And then that robot wakes up and can start building another robot. And part of this paper was a really interesting CAM problem where a robot could place a part, it could make another robot, or it could make a bigger robot, and it's how do you divide work over self-reproducing robots. And so this is building robots out of the functional voxels so the robots can make the robots. So those are using conventional actuators. So to refine that, here, this is an assembler of micromechanical systems. So this is like a sort of cross between a pick and place and 3D printer that's doing 3D construction of functional parts. And what it's building is this. So this is a motor. A rigid part is rigid, flexible is flexible. 2 flexible parts is parallel transport. 4 of those is a 4-bar linkage. Then a 1-bit actuator is 1 bit, but 2 1-bit actuators is cyclical motion. And then that turns into a stepping motor, a discretely assembled motor. But instead of the motor, and yeah, this is a slow motion of how it moves. Instead of the motor being a fixed thing, you have a building block of these small components, and you can assemble as many cylinders as you want in the rotor, whatever geometry. That was a fixed one. We've made walking robots out of those that locomote, and we haven't completed this, and this is another thing I'd like to get to potentially in this collaboration. This is a walking robot made out of these parts with the gripper to place the parts, and I want to get up to one of these being able to make one of these at that level. So not just the robot making the robot I showed you before has a coarse-grained circuit board and motor. This is now breaking those apart into their sub-building blocks. And then this was a project during his time in CBA year he had worked on. This project started with chips. The person at DARPA who led the program on chiplets. So the frontier of IC design isn't one big chip, it's making little chiplets and assembling them in multi-chip modules. That's in 2D, and he asked if we could do chiplets in 3D, if I could assemble 3D electronics. And so here we developed a cross between a pick and place and a 3D printer to build 3D electronic structures. And we're doing it at a number of different length scales. So this is an example of a design tool. And so Alan and Dimitar are working on this project, which is at the component level, we want to kill off PCBs and soldering by doing 3D assembly of electronic components. And then shrinking further, actually I'll show you further in a little bit. And so instead of all of the supply chains for integrated electronics and for PCBs and all of the stages to go from chiplets to system on chip to interposer to packaged part to discretes to PCB to boards to blades to systems, we want to span all of that in a single process of 3D assembly of integrated electronics. And so to do that, we've had to develop entirely new kinds of design tools for how you design 3D electronics, how you span all of those scales, and then these new fabrication parts to place carriers to one way, the CTO of Texas Instruments nicely describes this as VMD. Electronics today is based on SMD, surface mount. This is looking to replace SMD with VMD, which is volume mount, with sort of Lego, volume mount packages rather than surface mount packages. And we're doing that from CPU scale to wafer level chip scale packaging to state-of-the-art discretes are approaching early IC pitch. And the most aggressive version we're doing is a project where we're looking at when Lego becomes quantum. So these are nanoclusters at tens of nanometers. And at the very highest resolution, we're looking at the crossover between mechanically joining bricks and chemically making bonds to look at the core functionality of the integrated electronics to discretely assemble MOSFETs and all of the components in the integrated electronics at that scale. And so this hierarchy leads to the base materials we assemble into structural elements. We add with active elements to build actuators that make micro-robotic systems that build elements of larger robots that become assemblers that build larger structures. And in what I've shown you, we have examples of every stage in that hierarchy. Early on, I tried to go from the bottom to the top and found that didn't make sense. Instead, we're doing all of these in parallel. And to come is connecting these layers together to be able to go from the bottom to the top with assembly across scales. So to understand why that's needed, there's a lot of attention right now to an AI revolution. But there's another way to view it which makes more sense, which is if you look at a supercomputer as of about 2 years ago, and you look at a brain, as of about 2 years ago, the ops per second matched. And if you look at the storage in the computer and the, again, ops per second, there wasn't an AI breakthrough. What happened is the rate at which you could process data and the amount of data you could store and the sources of the data you could ingest crossed our brain about 2 years ago. And it shouldn't be a surprise you could then do things with the complexity of the brain because we have the degrees of freedom of the brain. And that's really what happened. It wasn't a new insight, it was a scaling story. But if you look at the chip fab making the supercomputer, it can do about 10 to the 10 or maybe now 10 to the 11 parts per second. While you're digesting your lunch, you're placing 10 to the 18 parts per second right now. And that comes from the ribosomes that are making your proteins are slow. They run at 1 hertz. You make an elephant 1 amino acid a second, but ribosomes make ribosomes. So a cell can have 1 trillion ribosomes. And so you get this exponential complexity of massively parallel serial fabrication, which is what makes it possible to make you. And so the AI revolution for your brain happened 2 years ago, but the AI revolution for your body is 8 orders of magnitude off. And so you need self-reproduction to cover that gap in fabricational complexity. And then I'm not talking about it here, but there's a really beautiful problem that I've done some work on, which is one of the oldest and most conserved parts of the genome are what are called Hox genes. And these are used in developmental programs. And so your body, your genome doesn't anywhere store the number 5 for 5 fingers. It stores a developmental program, and that's written in terms of concepts like you break symmetry and you climb gradients. And at the end of that, you have a hand. That's good for compression, but the main reason it's done is most genome edits are fatal or inconsequential but not interesting. Innovation in developmental programs is what lets you go from swimming to walking to flying. It's a beautifully conserved search space. And so we've done some work on, it's sort of tautological that as engineers, if you want to make a phone, you design the phone. And that's not what the body does. You design a developmental program that results in the phone. And that may sound semantic, but that's fundamentally the distinction that lets evolution work. And so we've done some work on morphogenesis in engineering design, which is how do we capture the artificial intelligence, not in our brain, but in our body, in how it does design discovery, which is central to closing these 8 orders of magnitude. Now, again, for history, this isn't a new insight. The real origin of this is von Neumann and Turing are credited for modern theory of computing. What the modern theory of computing neglects is they ended their life studying fabrication. So von Neumann studied self-reproducing automata, how a computation communicates its construction. And with Stan Ulam, that led to inventing cellular automata to model this. And it's a really beautiful, subtle problem. If you have a description of yourself, how do you transmit your description of yourself and then put yourself in it so it wakes up and starts operating? There's sort of a beautiful, subtle recursion that you have to implement to encode self-reproducing automata. And von Neumann didn't do it theoretically. He did it by construction in the CA world. And Turing ended life studying morphogenesis. The Evo-Devo problem, what I was describing in Hox genes, it's how do genes give rise to form? And so they both ended their life studying not fabrication as a computer controlling a tool, but this embodying of computation in construction. This is Santa Fe Institute did a beautiful series of classic papers in complexity with commentary. And I wrote, these are notes I wrote about von Neumann's automata. So if you want to think about the scaling, 1 Earth, 1,000 cities, 1 million towns, 1 billion people, 1 trillion things. There was one NC mill, MIT made the first real-time computer, the Whirlwind. One of those. There were thousands of mini computers used to create the internet. There were millions of hobbyist computers, billions of personal computers, now trillions of Internet of Things. MIT did the first NC mill in 1952. There's one of those. Today, thousands of Fab Labs. Those are like the mini computers. The Internet was invented decades before the iPhone. Fab Labs are the cost and complexity of a mini computer. And like mini computers, they're being used to figure out how do you live, learn, work, and play, if anybody can make anything. Then the machines making the machines are like the hobbyist computers. The early hobbyist computers weren't useful. They were personal. The earliest rapid prototyping of rapid prototyping aren't fabulous, but work, and now they're getting better. And then they still need global supply chains for the inputs. And so the assemblers reduce, let's see, you're made from an inventory of 20 parts, and that inspires me to try to do all of engineering with 20 parts, but now inorganic parts for the assemblers to make almost anything. There's a fun thing, I'm part of the bonus material for the movie The Martian. looking at how you start a civilization on Mars. And there I talk about sort of amino acids for engineering to do all of technology out of 20 parts. And then finally, to get to the exponential complexity, we need this recursion of self-reproduction, where the materials and the machines merge in these self-reproducing systems. And so this is a podcast where I talk about all of that. And then in this book, my younger brother led the biggest video game studio. My older brother led the National Labor Relations Organization. And in this, I describe the research roadmap for anybody to make anything. And then they're looking at the libertarian vision at the birth of computing didn't anticipate spam and fake news and income inequality. And the book is looking at how we shape all of this now so it doesn't then lead to the equivalent of all of that in the physical world, how we shape that revolution today. So that's a tour through digital to physical. And on another visit, I can talk more about current and future work going from physical back to digital, something Quentin does a lot of work on. And then I'll be visiting labs and meeting with Yuri's lab this afternoon under this MISTY project to look at collaborative work. One of the things we're looking at doing is, let's see if we go back to, is controls for these sort of systems, how an adaptive control can learn an arbitrary configuration. And one of the things I really want to do is I want to build a version of these micromechanical systems that's macromechanical, to make large-scale robots that don't require conventional motors and actuators, but have distributed intelligence in them, and ultimately get up to them being able to place their parts. And so we'll be exploring that today and over the coming year. So with that, I'll thank you and be happy to take questions.